Students. So I wanted to try to make a video working through some of these concepts from the review guide for you guys. So we'll kind of take a few of these, we'll kind of bounce around if we need to. All right, so the first page just contains a lot of terms and such, and you can find these in the textbook, or you can Google these if you wanted to. But you want to make sure that they are in the same terms that we've been using, because there's a calculus-based version of some of these, and there's an algebra-based version of some of these. Okay, so I don't need to look up these for you guys. You can look them up and write your definitions. Remember that these are probably where some of the true-false questions might come from. Make sure you know impulse and momentum and the impulse-momentum theorem, what an isolated system is, how we're just looking at collision between two objects and nothing outside of that, conservation of momentum, conservation of energy, work energy theorem, that kind of stuff. Okay. So getting into some of those short answer questions, I will not write out the answers completely, okay? So I'll just kind of write notes here and there. So how does impulse and the change of momentum compare? They are the same, okay? Remember, impulse is F delta T, and change of momentum is just delta P. They are equal. This is the impulse momentum theorem. The impulse is equal to the change of momentum. And we had different versions of this equation. If you wanted to have them, right, we had F delta P equals M delta V. And then these are the two linear versions. We also had the angular versions of these. Okay, so we had torque delta T is equal to I delta omega. All right, that was the version using your angular speed. And then the other one was torque delta time is equal to change in L, which is your angular momentum. So these are the angular versions of them. And I will have an equation sheet for you if you need these. Okay, so the next one here, we are considering a collision between a compact car and a full-size truck. How do the impulses compare between the two? How will the forces compare between the two? How will the accelerations compare between the two after the collision? Okay, the first two are the same. Impulse, F delta T, is the same for both of those cars in the collision. And then if we're kind of isolating that a little bit more, looking at the force, that is also the same. They're going to feel the same force. That's going to be the same exact time. Because they're going to be in contact with each other for the same amount of time. The one that's different is the accelerations afterwards, okay? The larger object will feel less acceleration afterwards. The full-size truck is larger, and so the change of momentum here, I guess the change of momentum is going to be the same, but the change in acceleration or speeds is going to be different because of the mass of the truck versus the car. A car is a lot smaller, so the velocity is going to have to change quite a bit more in order to be equal to the velocity change or the momentum change here, okay? So acceleration of the car is going to be much greater than the truck. All right, here, why is angular momentum important to an ice skater or a gymnast? That's because you need to understand how the center of gravity works, or your center of mass works, in order to control the speed of rotation, right? So if we have our gymnast and let's say they got their arms way out like that, they're going to go a lot slower than if they had their arms kind of tucked at their side, because their center of mass is spread out here. Here it's kind of contained right in the center, so they're going to spin faster here than they would here. So it's important to understand how angular momentum is connected to the center of mass. Okay, your center of mass is important. Okay, this question, they're different because you got to think of momentum being a vector, right? So you draw momentum vectors, one going that way, one going that way if you're going north and south. And then number 4, we touched on this a little bit in some problems where we did recoil, right? So we had the little spaceman with his little oxygen gun, and it's the same way with spaceships. They're burning rocket fuel, and so rocket fuel pushes out the back of the rocket, right, which propels it forward. So my fuel is going this way, rocket's going that way. So we have force pairs, equal and opposite reactions, okay? But we have the explosion of kerosene and oxygen or whatever we have to start the fire and make the rocket ship propel forward, and the gases propel out the back, okay? So this is what we call recoil. We could also consider this conservation of momentum. Because we have to have momentum conserved in order for that rocket to go forward, okay? And next one here, skateboarder traveling at 4.45 meters per second can be stopped by a strong force in 1.82 seconds and a weak force in 5.34 seconds. Mass of the skater and the skateboard is 53.6. What's the impulse on the skateboarder? What's the average force on the skateboarder in each of these stops? Okay, so you need the impulse on each one of these, okay? And actually the impulse will be the same, right? Because either way, we're going from 4.45 meters per second to a stop. So that means the impulse is going to be the same, but the force is going to be different, okay? So for the first one, we're just doing change in momentum. I guess for both of them, we're doing change in momentum. The skateboarder is 53.6 kilograms. And the speed is going from 4.45 meters per second to 0. So we do final minus initial. And we can go ahead and calculate the impulse. Okay, this will be a negative because they're coming to a stop. So we do 53.6 times negative 4.45, and you get an impulse of negative 238.52. And that's Newton seconds. Okay, that's your impulse, F delta T. Now you need to take this information, and then we're going to use the two different time values to find the average force on each of the stops. Okay, so let's do the faster of the two stops right there. So F times 1.82 seconds is equal to negative 238.52 Newton seconds, divided by 1.82 seconds, divided by 1.82 seconds, and we get a force of negative 131.05 newtons, okay? So go ahead and get the other one. It's going to be a lot less than that because it's more of a gentle stop, okay? Because we're going to be dividing by 5.3 rather than 1.8. Okay, next one here, we're going to be working with angular momentum and torque and time, so that means we're going to be working with angular impulse. Okay, so what's the angular impulse on the object? Angular impulse is torque delta time equal to the moment of inertia of the object times the change in angular velocity squared. Okay, so we have an angular momentum of 8.9. So actually we want to use the other version of this because we're given the angular momentum. They made it a little bit easier for us. So torque delta time is equal to change in angular momentum. Okay, so we're slowing to a stop in 5.2 seconds. What's the angular impulse? We just need to go from here to 0. Okay, so that's pretty simple. Change in angular momentum is going to be 0 minus 8.9 kilograms meters squared per second. And that's just a negative 8.9. Okay, and I can put that decimal in the right place. Okay, and remember we got to have our units correct when we're talking about impulse. Because that's what we were looking for first here. What's the angular impulse, which is just a change in momentum, right? These are equal. So we have to make our units so they reflect angular impulse. So they are Newton meters second, right? Because torque is a Newton meter and time is a second. So we have a negative 8.9 Newton meter second for angular impulse. And then we want average torque on the object. So now we're going to be using this whole thing here. Okay, so it's torque times our time that we're given, 5.2 seconds, is equal to negative 8.9 Newton meters second. Divide both sides by 5.2, and we'll get what we're looking for. 1.711. So our torque is equal to 1.71 Newton meters. Okay. So for number 7, you should be able to work through this, considering I just worked through 5 and 6. This is going to be an impulse problem. Okay. So the ball is going from 26 meters per second to 38 meters per second. So that's what you're going to be doing for your change in velocity. If you did change in momentum, that's going to be the mass times change in velocity, which is 38 meters per second as your final velocity minus 26 meters per second as your initial velocity. That would be your change in momentum. You want to draw a quick sketch here. Okay, so arrows showing the ball's momentum before and after the ball gets hit, so you'd probably do 2 sketches here. One of them with the baseball going this way right before the bat hits it. Okay, maybe there's a bat. And then the other one after the bat hits it, baseball momentum vector going that way. Okay, so we have a change of momentum. So go ahead and figure this one out. Impulse, use the equation that I just gave you for the last one. And you have, this is 0.8 milliseconds. Okay, so that might be a little different for you guys. But remember how we go from milliseconds to seconds, right? Milli is times 10 to the negative third, so that's going to move my decimal place 3 to the left. So it's 0.008 seconds. You want to make sure that we're using seconds for our units. All right, number 8. We're working with collisions here. So number 8 and 9 will be working with collisions. So railroad car A, that's 6275 kilograms, is going east. And the railroad car B is going east along the same track. 2 railroad cars hit and stick together. Assume the track is frictionless. How far do the 2 railroad cars move immediately after the collision? So this is a conservation of momentum problem. We got our initial momentum is equal to our final momentum. Okay, in the beginning, initial momentum, we have 2 separate objects. So we have car A and then we have car B. In the end, they're stuck together. So it's one object with combined masses. Okay, so momentum of car A plus momentum of railroad car B. That's going to be what we have in the beginning. And then in the end, we're going to have momentum of car A plus car B because they're stuck together. Okay, so car A, 6275 kilograms times its speed, 6.5 meters per second, plus car B, which is 5155 kilograms, times the speed of car B, which is 3.8 meters per second. That is going to be equal to the combined masses times the velocity. So we have 6275 kilograms plus 5155 kilograms times that velocity in the end. Okay, so now from here it's just a lot of calculator work. So we're going to add those together, divide by the combined mass. So on the left we get a value of 60,376.5, and that's kilograms meters per second, that's momentum. And on the right we're going to get 11,430 times the final velocity, divide both sides by 11,430, and we get a final velocity of 5.28 meters per second.